I'm Steve Harms, Medical Director of Aurora Imaging Technology and your host on this presentation, SpiralRodeo, Revolutionary Technology for Breast Imaging. SpiralRodeo is perhaps the biggest breakthrough in breast MRI in the last decade. It provides unprecedented improvements in image quality that should significantly improve the diagnostic capability of breast MRI. The unique image acquisition technology allows the simultaneous generation of high temporal and high spatial resolution information. This presentation will summarize the clinical and technological features of this extraordinary new breast imaging method. Here is an example of a patient who presented with a unilateral nipple discharge. The maximum intensity projection, MIP, of the pre-contrast non-spoiled SpiralRodeo shows fluid as hyperintense. The MIP depicts an MRI galactogram of the dilated ducts in the right breast. These ducts extend into the superior breast, the site of the ductal carcinoma in situ, DCIS. Notice the tiny branching ducts that can be seen on the high-resolution SpiralRodeo images. These images are generated routinely on the Aurora system and do not require an additional scan time. The post-contrast spoiled SpiralRodeo shows asymmetric enhancement within the superior right breast in the region of the DCIS. As we move into the thin slices, you will see the clumped enhancement that is arranged in a branching linear pattern. Without high resolution, you would only see regional enhancement, a relatively nonspecific finding. The high resolution of SpiralRodeo demonstrates characteristic branching enhancement in almost every case of DCIS. Improved image quality results in better, more confident diagnosis. Specifically, what are we talking about when we say that SpiralRodeo is a significant breakthrough? SpiralRodeo is a new way of acquiring breast MR images. It is extremely efficient, providing 3 times better signal-to-noise ratio, SNR. This is equivalent SNR increase to going from 1.5 Tesla to 4.5 Tesla. At Aurora, we use this SNR gain to improve the resolution by 4-fold over what we were doing with our old 3DFT Rodeo, which was already one of the highest resolution scans in the industry. Higher contrast is also achieved with SpiralRodeo. Better contrast provides better demonstration of subtle lesions like DCIS. The contrast resolution is so solid that a CT-type image processing technique such as surface rendering and volume rendering are now possible using breast MRI data from SpiralRodeo. The inherent acquisition features of spiral reconstruction allows the simultaneous generation of both high temporal and high spatial resolution information. Why do we need improvements in contrast and resolution? Do you see a lesion? This is a 3mm slice generated with a 3DFT Rodeo technique. DCIS is present in this image but cannot be seen due to volume averaging. Now look at the same area, but with a slice thickness changed to 1 mm. The branching contrast enhancement pattern of DCIS now stands out. The voxel size is reduced to 1 mm thickness, and the proportion of DCIS in the voxel is sufficient to register as hyperintense signal. Notice that the downside of thin slices is lower signal to noise. The images are more noisy. As we try to make further improvements in resolution, we will also need to improve the signal noise to support the smaller voxels. This 3DFT matrix is 280 by 300 by 128 and is about the limit in resolution that this signal noise can support. Another advantage of thin voxels is the ability to do high-quality image reformations. The breast is not oriented in orthogonal planes, axial, sagittal, and coronal. In general, the breast is oriented with converging planes centered on the nipple. However, as in this example, some ducts are oriented in other planes. The ability to reformat images in any desired plane without a loss in image quality is a significant advantage for breast diagnosis. Thin slices also have the advantage of being able to generate high-quality maximum intensity projection MIP images in any desired angle. Volume averaging also affects MIP images, since the brightest voxels are displayed. If sufficient brightness is not achieved due to the volume averaging, then the voxels will not be displayed on the MIP. While we rely on dynamics to identify cancer, DCIS infrequently washes out. In this patient, persistent enhancement that is most commonly associated with benign enhancement is seen. Since most CAD programs rely on dynamics for lesion identification, CAD would miss this DCIS. The only answer is high-quality images for this diagnosis. The reason that DCIS is so difficult to see on many breast MR imaging methods can be easily understood by reviewing the histology of DCIS. DCIS consists of tumor cells that are confined by the basement membrane of the duct. The duct is surrounded by normal tissue. Voxels that are large will include sufficient amounts of surrounding normal tissue that will average with the tumor. The overall measurement for the voxel intensity will be lowered and may be below the threshold for visualization. Volume averaging effects are reduced with smaller voxels and higher contrast. SpiralRodeo is designed to produce higher contrast and higher resolution. I will review some of the key points in the diagnosis of DCIS with breast MRI. DCIS is defined as a tumor within the duct, confined by the basement membrane. These ducts are surrounded by normal tissue. The biggest problem with MRI diagnosis of DCIS is volume averaging. To do a better job, you need higher contrast and higher spatial resolution. Remember, voxels are three-dimensional. Thick slices can lead to volume averaging. Washout is not commonly present in DCIS. Many CAD programs cannot be relied upon to detect DCIS. Higher resolution not only allows the lesion to have sufficient signal to be seen, it also provides better image reformation and maximum intensity projection MIP images. High-quality breast MRI should see more DCIS than mammography. Incidental DCIS picked up at pathology is only calcified in a third of cases. Yet, of the DCIS found on mammography, 90% is calcified. We are probably missing 2/3 of DCIS cases with mammography. A key component of SpiralRodeo technology is the Rodeo pulse sequence. Rodeo stands for Rotating Delivery of Excitation Off Resonance. Advantages of Rodeo are improved efficiency, fat suppression, and ductal tissue background suppression. The technical requirements of Rodeo are a homogeneous magnetic field and transmit-receive RF coils. Why do we need fat suppression? To avoid the snowman in the snowstorm effect. Tumors enhanced or turned white with contrast on T1 weighted MRI scans. Normally, fat on T1 scans is white. If we have a white tumor in a white background, we cannot see it. With fat suppression, the bright fat signal is diminished, allowing us to visualize the tumor. Chemical shift fat suppression requires a highly homogeneous magnetic field. Magnetic fields are made homogeneous by a process called shimming. The magnet is typically designed to have a certain shim characteristic by the factory. Further tuning of this shim is typically done for each patient. On the left is an examination performed on a whole body machine where the fat cannot be suppressed due to a bad shim. The left breast has hyperintense fat due to poor fat suppression. On the right is an aurora examination where not only is the fat of both breasts suppressed, but the axillary regions are also suppressed bilaterally. This is the result of a specially designed magnet with an ellipsoid shim and tuning technology called super shim that specifically tunes the shim for each patient. Most whole body magnets are designed to have the most homogeneous region or sweet spot to be a sphere centered in the bore of the magnet. For an off-center field of view, the sweet spot can be shifted and adjusted using scanner shim technology. This is why many prefer to do only single breast examinations. The shim characteristics cannot accommodate the large field of view needed to fat suppress both breasts. More recently, in an effort to accommodate dual breast examinations, manufacturers may allow tuning of two regions of interest with the scanner shim technology. While an improvement over a single field of view, the shim is still limited when compared to the shim at the magnet isocenter. Also, most auto shim technology is designed around spectroscopy applications, not fat suppressed imaging. Hot spots in images due to inadequate fat suppression remain a major problem in breast MRI. The Aurora magnet is unique in the industry by providing an ellipsoid sweet spot that is centered on the breasts. The sweet spot is shifted from the usual isocenter anteriorly. The usual spherical sweet spot is expanded in the mediolateral dimension and reduced in the superior-inferior dimension. While this geometry would not be acceptable for many whole-body applications, it is ideal for fat-suppressed imaging of both breasts. Most whole-body systems that have automated shim tuning systems are designed primarily for spectroscopy. Spectroscopy usually analyzes proton resonance over a small region like a brain mass. Often these schemes are suboptimal for tuning fat suppression over a large field of view that includes both breasts. The Aurora Super Shim uses a proprietary image-based shim system that is designed specifically for chemical shift-based fat suppression. A model display of the shim is provided for the technologist's verification. Using Super Shim, the Aurora system is shimmed for each patient so that efficient, reproducible fat suppression is routinely achieved through both breast and axillary regions, regardless of patient size and configuration. Another hardware feature that is unique to the Aurora system is the RF coil. These coils are designed to provide a large field of view that includes both breasts and axillary regions. This coil provides a homogeneous distribution of RF and practically eliminates hot spots. A feature that is not offered elsewhere in the field is a separate localized transmit coil. This coil improves efficiency by eliminating the need for selective excitation gradient pulses. It also allows the use of the rodeo pulse sequence. The use of non-selective sequences like rodeo are not possible using body coil transmission as employed by whole body systems. The trend of most whole body systems is toward phased array receive coils and parallel imaging. This concept uses multiple smaller coils. Smaller coils have a better SNR, signal-to-noise ratio, but less coverage. The coverage issue is addressed by adding more coils. However, smaller coils have poor homogeneity and more hot spots are produced. Parallel imaging is used to improve resolution and/or reduce the scan time. Parallel imaging is not done without a cost. The price for parallel imaging is more artifacts and lower signal-to-noise ratio. While parallel imaging is a clear choice for high SNR applications like vascular imaging, the use of parallel imaging for a low contrast situation like breast MRI can be problematic. In this example, an image acquisition using phased array coils and parallel imaging on the left is compared with a large field of view transmit-receive coil on the right. Parallel imaging has ghost artifacts from the arms, wrapping in the field of view. The breast images are inhomogeneous because of small phased array coils. The large field of view transmit-receive coil provides homogeneous signal and good visualization of the axillary regions. Multiple coil arrays are tuned to the average size of breasts that are likely to be imaged. Unfortunately, breast sizes vary greatly. Small and large breasts pose major problems for these systems. The large field of view transmit-receive RF coils are capable of imaging large and small breasts equally well, as shown in these examples. Mastectomy patients are often a problem with multiple coil arrays due to the asymmetric filling. Here are some examples of patients that were imaged with the large field of view transmit-receive coils. Increasing use of neoadjuvant chemotherapy and sentinel node procedures have made MRI evaluation of lymph nodes very important. This patient presented with microcalcifications on screening mammography. Based upon the mammogram, this patient was thought to have DCIS. No adenopathy was recognized. Before the stereotactic biopsy, this breast MRI using SpiralRodeo was obtained. This projection view shows the abnormal enhancement in the right breast and multiple enlarged lymph nodes. Branching enhancement is seen in the breast consistent with DCIS. However, the axillary lymph nodes were enlarged and the fatty hilum lost. Based upon breast MRI, the breast and the axillary lymph nodes were subjected to needle biopsies. DCIS was found in the breast, but infiltrating carcinoma was present in the lymph nodes. Because of this diagnosis, the patient was spared a sentinel node procedure. She had a lumpectomy and a node dissection. The Aurora transmit-receive breast coils are built into the patient table. In addition to better performance, this arrangement frees up the magnet bore to make more room for the patient. The term pulse sequence refers to the RF pulse and gradient waveform instructions that are designed to excite and receive MRI signals and achieve image contrast and encode spatial information. In the breast, specific contrast features to be imaged are fat, ductal tissue, silicone, fluid, and neoplasm. Ideally, these should be imaged with as much contrast and specificity as possible. There are always trade-offs in breast MRI. In breast MRI, the biggest trade-off is spatial resolution versus temporal resolution. To get better speed, resolution is often sacrificed, and vice versa. The combination of the pulse sequence and the acquisition method will determine efficiency and how closely the methods achieve temporal and spatial resolution goals. Fat suppression is one of the fundamental contrast mechanisms achieved by most breast MRI pulse sequences. The reason why fat suppression is needed is that fat is bright on T1 weighted images due to a short T1. When a contrast agent is given, the T1 of tumors shortens and the tumors become hyperintense. To avoid the snowman in a snowstorm effect, either subtraction or suppressing fat signal is needed. Subtraction is straightforward and easily achieved. However, if motion occurs, subtraction can generate artifacts that obscure a lesion. Subtraction, by definition, eliminates much of the signal noise, resulting in low-resolution, noisy images. For the most part, modern MRI protocols use subtraction as an adjunct to fat suppression, not the only method for imaging an enhancing lesion. Fat suppression is now preferred due to the cleaner, higher resolution images. All manufacturers now employ some form of fat suppression for breast imaging. The quality, of course, varies with the vendor. Most chemical shift-based fat suppression methods are subject to magnetic and RF field inhomogeneity. Fat saturation, or FAT-SAT, is the most commonly used fat suppression method. It is technically straightforward, but subject to hotspots due to magnetic field inhomogeneity. FAT-SAT incompletely suppresses fat. The quality of fat suppression is heavily dependent upon the TE, or echo time, since some recovery of signal occurs before the echo can be formed. Rodeo is a water excitation method. Fat is selectively not excited. In MRI, if you don't want to see it, it is better not to excite it. Rodeo is very efficient. It does not require a separate RF pulse before the excitation pulse. Rodeo is dependent upon good magnetic field homogeneity. This is an example of a patient who moved between the pre- and post-contrast images. The subtraction has so much artifact that the lesion is hard to see. The MIP of the subtraction barely depicts an enhancing lesion. Many users only do MIPs of subtracted images because subtraction eliminates many of the artifacts induced by poor magnetic and RF field homogeneity. The same subtracted image is compared with the immediate post-contrast image, where additional lesions along the lateral aspect of the breast are well seen. The MIP of the subtracted images and the MIP of the immediate post-contrast images are compared to show the improved depiction of the lesion on the fat-suppressed post-contrast images. In MRI, improved signal to noise is often achieved by going up in field strength. Going from 1.5 Tesla to 3 Tesla would approximately double the signal-to-noise ratio. Coil design improvements, such as going from a body coil to a surface coil, can also be used to gain signal-to-noise. Pulse sequences are commonly used to implement desired contrast effects. Although not commonly recognized, the signal-to-noise can also be boosted by improved pulse sequence efficiency. To understand this effect, we need to review MRI pulse sequences. We begin with an RF excitation pulse. For almost all commercially available breast MR sequences, this is a sync pulse. For 3D applications, this is usually a narrow flip angle that is typically employed on gradient echo sequences. A gradient is usually applied during the excitation in order to select a slab for 3D imaging. This gradient pulse is in the slice direction. This gradient pulse is followed by a compensation pulse to maintain phase. In order to refocus the RF and form an echo, a gradient pulse is needed. An echo is formed on the RF line after a time delay called the echo time, or TE. A frequency encoding gradient is applied during the echo. Phase encoding gradients are applied in the in-plane, phase, and slice directions. Since the amount of gradient applied varies with the projection, these are shown as multiple lines. Typically, these are compensated after the echo. The repetition time, or TR, is the time from the beginning of the sequence to the start of the next sequence. Now we are finished with a typical gradient echo sequence. Changes are made for breast imaging. In order to reduce the TR, a fractional echo is often used. This shortens the TE. The frequency encoding gradient shortens. While increasing the number of TRs that can be obtained in a given time, the SNR is reduced because of two reasons. One factor is the shorter sampling interval. The other is because of conjugate symmetry used to calculate the first part of the echo, which is not sampled in fractional echo schemes. Since that part of the echo is calculated from the last half and not actually sampled, any artifacts in the second half will be propagated in the first. Next, we need to add fat suppression. Chemical shift fat saturation, or FAT-SAT, is the most common. This is usually applied as a 90-degree RF pulse before the excitation pulse. A spoiling gradient is applied to dephase the excited fat spins. This results in a longer TR. The relative time that signals are acquired during the sampling interval is decreased to about 9% of the overall sequence, half of what it was without fat saturation. Fat suppression is necessary, but the price is lower efficiency and lower signal noise. When we visit the reconstruction methods, we will see how some manufacturers attempt to compensate for less efficient pulse sequences by alternative reconstruction schemes. FAT-SAT usually results in less complete fat suppression because fat magnetization recovers between the time the fat is excited and the echo. The shorter this time interval, the better the fat suppression. This is why it is important to have high-performance gradients when using FAT-SAT. With these gradients, the ramp times and gradient durations are less, allowing a shorter time between the fat excitation pulse and the echo. Here's an example of a small enhancing lesion in the left breast seen on a 3DFT rodeo image. A mastectomy was performed on the right. Here is the same lesion shown on a FAT-SAT image. Notice the difference in fat suppression. The ductal tissue is not suppressed on this image. Image reformation is not useful because the slices are too thick. Likewise, MIP is only useful in the acquisition plane. Subtraction is heavily used for interpretation because of artifacts and contrast problems on the original images. Rodeo actually excites water and selectively does not excite a narrow range of bandwidths, typically fat. It works like this. Fat and water magnetization vectors are initially aligned with the applied magnetic field. A 45-degree sine excitation pulse is applied. Fat and water are both excited to 45 degrees. Because water resonates at a slightly different frequency than fat, the water vector moves out of phase from fat. Then a second 45-degree sine pulse is applied in exactly the opposite phase from the first RF pulse. The fat vector sees this RF pulse as exactly the opposite of the first, and the fat vector is driven back to its original longitudinal position. Water, which has moved out of phase, sees the next RF pulse as additive and is further excited. The magnetization that rotates in the horizontal plane produces the radiofrequency signal that is measured in MRI. Ductal tissue suppression is important. Many women who need breast MRI for diagnosis also have dense breasts. Ductal tissue can impair visualization of lesions. Lesion ductal tissue contrast can be improved with a technique called magnetization transfer contrast, or MTC. MTC pulses are typically applied as a pre-pulse before the beginning of the sequence. While widely employed by most manufacturers to improve the quality of MR angiography, MTC is infrequently used for breast imaging due to the additional time needed for the MTC pulse and the associated increased scan time. Rodeo integrates MTC into the standard excitation pulse. No pre-pulse is needed on rodeo sequences. When we talk about excitation on most MRI scans, we are typically talking about free water and fat resonance. There is, however, a very broad resonance background of bound water. This bound water largely consists of water molecules that are highly associated with protein. High power excitation of this bound water produces magnetization transfer contrast, resulting in suppression of ductal tissue in the post-contrast images due to saturation of the long T1 spins. Most MTC excitations are produced with a separate pulse at some distance from the free water resonance. This is done to avoid contamination of excitation with the free water resonance. A MTC pulse is typically applied before the sequence RF pulse. The MTC pulse is typically of long duration and far off resonance relative to the usual sequence excitation pulse. For rodeo, we replace the sync RF pulse with a reverse sine rodeo pulse. Rodeo has built-in magnetization transfer contrast, so we can shorten our sequence by taking out the MTC pulses. When we replace the sync pulse with the rodeo pulse itself takes more time, but we can eliminate the fat-sat pulse and its gradient pulses to significantly decrease the overall scan time. In addition, rodeo does not use selective excitation, so these pulses can be eliminated. As a result, rodeo significantly improves the pulse sequence efficiency and the quality of fat and ductal tissue suppression. Before we move to the technical details of SpiralRodeo, let's review a clinical example. This patient had a recent excision of a cancer and pathology reported positive margins. The pre-contrast, non-spoiled SpiralRodeo shows the excision line on the skin of the left breast. As we move to the maximum intensity projection images, we see hyperintense fluid in the seroma at the excision site. This fluid is bright because of the long T2 of pure fluid. Because many of the gradient pulses are eliminated using rodeo, these non-spoiled, fluid-weighted images are routinely produced. These images are more specific than T2-weighted images. Some tumors are bright on T2-weighted images, but not on non-spoiled rodeo images. In addition, these images have significantly higher resolution and are produced in exactly the same image geometry as our post-contrast images. This geometric efficiency allows utilization of this highly specific information for our Aurora CAD display technology. Despite the significantly higher quality of the non-spoiled rodeo images, their overall scan time is reduced since the inefficient, low-resolution T2-weighted images are eliminated from the scan protocol. The post-contrast spoiled rodeo images in this patient depict the thin margin of the seroma without any residual tumor. Because SpiralRodeo has nearly equal resolution in all three planes, images can be reformatted in any desired plane without any perceptible loss in resolution. You are no longer concerned about which plane to acquire the images. You get any conceivable plane with SpiralRodeo. MRI images are generated from multiple spatially encoded projections. Because of the ability to generate thin slices with gradient echoes, 3D has largely supplanted 2D for breast imaging. There are several 3D solutions that have emerged for breast imaging. 3D Fourier transform, or 3DFT, is the standard method used on almost all breast imaging protocols. The biggest trade-off with 3DFT is that it is time-consuming, particularly if performed with high resolution. The need for bilateral breast imaging and dynamics have resulted in a sacrifice in image quality on many protocols. Slices are getting thicker and the signal to noise lower. An attempt to improve acquisition efficiency resulted in the development of elliptic-centric sampling of reconstruction space. With elliptic-centric, only a limited number of projections are obtained during the desired time period. The finished images are reconstructed with the use of additional projections gathered during a less critical time period. The trade-offs for this approach are poor contrast and image artifacts. Spiral is a major departure from 3DFT. It possesses some inherently significant improvements in image quality, but requires specific hardware. What is SpiralRodeo? Spiral is a different way of spatially encoding information for MRI reconstruction. The reason for doing spiral reconstruction is that it is highly efficient. It is actually about 3 times more efficient than 3DFT, the standard reconstruction method used on most scanners. In signal-to-noise terms, this is like going to 4.5 Tesla in field strength. It provides superior contrast resolution because the center of reconstruction space is sampled on every projection. And it produces higher temporal resolution. No longer is there a debate of which to choose. High temporal and high spatial resolution are achieved in the same scan. There are specific technical hardware requirements. Precision gradients are needed to play the complex spiral gradient waveforms without distortion, and faster computers are needed to handle the extensive data that is generated with spiral acquisitions. Another way to improve efficiency is by alternative methods of image reconstruction. Many manufacturers use these alternatives to compensate for losses in pulse sequence efficiency. In the following description, you will see how the combination of spiral reconstruction and the rodeo pulse sequence work together to achieve unprecedented efficiency, resulting in a significant gain in the signal-to-noise ratio and image contrast. Basically, K-space is composed of a grid of projections in 3 planes. To reconstruct an image, we need to fill this grid with projections. Not all projections are equal in their contribution. The center of K-space contributes most of the contrast, while the periphery contributes most of the image resolution. Typically, K-space is filled a line at a time for each TR. Here we are sequentially filling with each TR from the bottom to the top of K-space. If we want 128 lines of resolution in this image, we need to fill 128 lines of K-space, and the scan will be 128 times the TR long. If we double the resolution, we will double the scan time. For 3DFT, we will also encode in the slice dimension. Now if we want 64 slices, we will need 64 times 128 projections. You can see how increases in resolution significantly increase the scan time. Notice how we can vary the contrast of the image by changing the sequence of filling K-space. In fast spin echo, we fill reconstruction space with echoes at different TE values. If we start at the first TE in the periphery of K-space and end with the longest TE in the center of K-space, an image will be reconstructed that is weighted toward the last echo. Remember that the center of K-space contributes most of the contrast. Because the last echo is heavily T2 weighted, the image will have mostly T2 weighted contrast. If we change the filling of K-space and start with the first echo at the center and end with the last echo at the periphery, we will reconstruct an image that will be dominated by the first echo contrast. This image will have mostly proton density character. Although image contrast is altered by fast spin echo schemes, it is not done without a price. The price is image blurring and contrast ambiguity. While that may be acceptable for some applications, in breast imaging, where the goal is to evaluate small, low-contrast lesions, these trade-offs are often unacceptable. Image blurring and lower contrast will often result in lower lesion conspicuity. The K-space filling games have reached their pinnacle with vascular imaging. where rapid capture of the center of K-space as the contrast passes have allowed the generation of high-quality MR angiographic images. One of these methods is called elliptic-centric K-space sampling. In this application, only the center of K-space is captured during the contrast bolus. The remainder of K-space is filled by projections that are obtained on a pre-contrast scan. The trade-off for this type of reconstruction is image blurring and lower contrast. Since most of the background tissue is suppressed relative to the arteries in MR angiography, these trade-offs are very acceptable. Elliptic-centric K-space sampling is also used in some breast imaging sequences. The center of K-space is sampled 4 times during the dynamic phase of the contrast bolus. To reduce contrast problems, the additional projections used to fill the remainder of K-space are obtained at the end of the acquisition rather than before, as in MR angiography. In this example, all 5 images share information from the periphery of K-space. Of course, higher resolution images are generated in a shorter period of time than if the entire K-space were filled for a single image set. However, this K-space filling scheme reduces overall contrast and increases blurring. The lower contrast and image blurring will impair the detection of low contrast lesions like DCIS and lobular carcinoma that are often intermixed with normal breast tissue. K-space does not have to be filled line by line as in 3DFT. Spiral starts at the center of K-space and progressively extends to the periphery. Much more of K-space is covered in a single projection. In fact, some cardiac applications of spiral imaging actually generate an entire low-resolution image from a single projection. For breast MRI, where higher resolution is needed, multiple spiral projections are interleaved, each covering a different course through K-space. The improved efficiency of spiral is evident. For 128 or 256 lines of resolution on a 3DFT acquisition, it requires 128 or 256 projections respectively. We typically, with a spiral, generate 512 by 512 resolution with only 32 spiral projections. Another important aspect of spiral imaging is that the center of K-space is sampled on each projection. Remember that the contrast of the image is largely contributed by the center of K-space. The projections for a 3DFT image typically only scan through K-space during the center of the scan. For a 4-minute scan with 3DFT, only the time around 2 minutes will cover the center of K-space. If the contrast bolus arrives sooner or later, then the image contrast will suffer. For spiral acquisitions, it doesn't make any difference when the bolus arrives, since the center of K-space is covered on each projection. This serves to improve the contrast to noise ratio, since the center of K-space is essentially oversampled and averaged over the entire scan. This is why the contrast of SpiralRodeo is so solid. It resembles a CT scan in purity of the contrast and allows us to do CT-like image processing such as surfaces and volume renderings. Let's review our pulse sequence diagram. When we start with a FAT-SAT 3DFT, we first change the RF pulse to rodeo, then delete the FAT-SAT pulse and gradient pulses. Then we delete the selective excitation pulses. Now we're ready to change to spiral. The biggest change is that the frequency encoding gradient is no longer stationary. This is where we play the spiral gradient waveform. We no longer use the in-plane phase encoding between the RF pulses. A spiral gradient waveform is played in this direction, but is now moved to the same time as the echo. In 3DFT, the echo sampling interval is decreased to shorten the TR at the expense of signal to noise. With Spiral, the echo is typically lengthened to sample more of K-space and improve the signal to noise. With Spiral, a fractional echo is always used. Conjugate symmetry is not needed to calculate the front half of the echo. Notice that with SpiralRodeo, a significantly greater portion of the sequence is spent listening to the echo compared with the standard 3DFT. With a standard FATSAT, only about 9% of the TR time is actually spent gathering signal. With Spiral, this time increases to 47%. This is one reason why SpiralRodeo significantly increases the signal-to-noise ratio compared to traditional 3DFT scans. How does SpiralRodeo improve our clinical diagnostic capability? Here's a patient with a spiculated mass on mammography. This was suspicious for a small cancer. No suspicious microcalcifications were seen. Here's a SpiralRodeo examination of this same patient. On the projection images, we see the mass with a similar size as depicted on the mammogram. The mass has spiculated margins typical of an infiltrating carcinoma. However, what was not appreciated on the mammogram is this large area of regional enhancement inferior to the index lesion. Is this benign or malignant? We can tell more accurately as we move to higher resolution slices. Now we see that this enhancement is linear and branched. This is typical of DCIS. We almost always see branching enhancement in cases of DCIS on SpiralRodeo images. Linear and branching enhancement is infrequently seen on lower resolution images. Many breast MRI methods that employ low contrast, low resolution, thick slices will not see DCIS at all. The solid contrast resolution of SpiralRodeo allows the generation of excellent MIP images. This pre-contrast SpiralRodeo depicts the hematoma following vacuum-assisted biopsy in the left breast, the fluid in the ducts in the left breast, and the extensive cysts in both breasts. Notice the excellent fat suppression and ductal tissue suppression that allows superb visualization of both breasts and the chest wall. High-quality dynamics is a desirable feature since there is a general trend for infiltrating carcinoma to wash out and for benign lesions to have persistent enhancement. In an attempt to get faster images and better dynamic curves, many breast protocols sacrifice image quality. An advantage of SpiralRodeo is that many points on the dynamic enhancement curves are generated while improving overall image quality. We mentioned previously that one of the limitations of spiral acquisitions is the need for a different kind of gradient. This would be an opportune time to review gradients. Gradients are smaller, rapidly switched magnetic fields that are used principally to encode location. Gradient performance is typically measured by amplitude and rise time. These performance parameters are usually limitations for MR angiography, echoplanar imaging, and functional neuroimaging. High performance is usually achieved at the expense of gradient linearity or warping. Gradient warping results in spatial distortion. This distortion can be corrected to some extent with reconstruction techniques. However, gradient distortion is a major limitation for spiral acquisitions, since precise gradient waveforms must be played out. Lack of precision in the gradient leads to image blurring. Hence, spiral reconstructions rely on precision gradients. The gradient changes the magnetic field on one side of the magnet bore compared to the other. A typical whole body gradient has distortion or warping. The precision gradient provides a linear ramp across the bore. The image on the right is an actual image generated with a whole body system using dual gradients. The bites on both sides of the image show the extent of gradient warping. This amounts to several centimeters of distortion. The image on the left is from the Aurora scanner with precision gradients. A 44-centimeter phantom with cubes is accurately depicted without any significant distortion. The Aurora gradient is specified to have less than 1 millimeter of distortion over 44 centimeters. This precision gradient is handmade at the Aurora factory in North Andover, Massachusetts. This gradient manufacture is one of the unique features that makes spiral acquisitions possible. This patient had a breast cancer in the past treated with lumpectomy and radiation. She returns with this mammogram that shows 2 masses, possibly representing recurrent disease. They appear well separated from the chest wall. No adenopathy was seen. Notice the clip at the site of the prior lumpectomy. The surface rendering of the SpiralRodeo data shows the old skin incision site. Deep to this site, we see multiple areas of abnormal enhancement within the breast, probably representing recurrence. A total surprise was the abnormal enhancement extending to the chest wall. This disease extends deep to the pectoralis muscle. Involvement of the sternum is seen. The disease actually extends to the pericardium. The site of the prior lumpectomy actually does not enhance. Had the biopsy been performed using the clip for guidance, the cancer could have been missed. Notice the extensive adenopathy. SpiralRodeo provides excellent depiction of the axillary regions, the internal mammary regions, and the chest wall. SpiralRodeo has the following advantages. 3 times the signal-to-noise ratio of a 3DFT examination using standard rodeo. This gives us the signal-to-noise equivalent to a 4.5 Tesla magnet. The SNR improvement is used to generate a 4-fold improvement in resolution. Oversampling the center of K-space provides a 2-fold improvement in contrast. SpiralRodeo provides simultaneous generation of higher spatial resolution and higher temporal resolution images. Clinically, this translates into better, more accurate depiction of subtle lesions and better anatomic characterization. DCIS and lobular carcinomas are more reliably imaged. SpiralRodeo requires some specific hardware. The magnetic field must be very homogeneous. This is achieved with a factory-built and unique ellipsoid homogeneous region. Tuning for each patient is performed with image-driven shimming software called SuperShim. Specifically designed transmit-receive radiofrequency coils are built into the patient table. These provide homogeneous RF transmission and reception covering a broad volume that includes not only both breast but also the axillary and internal mammary nodal regions. This coil improves the pulse sequence performance by eliminating the need for selective excitation. Aurora proprietary precision gradients provide low distortion gradient waveforms that make spiral acquisitions a reality. These precision gradients also improve the accuracy of interventional procedures. Spiral acquisitions are computationally intensive. The image reconstruction engine uses 4 parallel Xeon processors. The Aurora CAD display system is also upgraded to accept the higher resolution large data sets of SpiralRodeo. What you've just seen is only the beginning of the SpiralRodeo revolution. The improved efficiency of the SpiralRodeo platform will enable even greater capabilities for breast MRI diagnosis in the future. SpiralRodeo is an exclusive product of Aurora Imaging Technology and only available on the Aurora dedicated breast MRI.